Hello everybody. In this notebook, we'll go over convolutional neural networks. These kinds of neural networks are used in tasks like image classification, object detection, and image segmentation. In fact, they were invented for image and video analysis. So in this notebook, we will first download a data set and then extract the data set, make it useful for training, and then we will create a model architecture, a very simple convolutional neural network architecture, which will be trained using the dataset we have downloaded. And then we will also learn how to evaluate this model that you have just trained. And that's about it. So let's get started with this notebook. All right, so this is our notebook. The dataset that we are going to download is the 10 monkey species dataset. It consists, as the name suggests, dataset of 10 different kinds of monkeys, and we are going to build this convolutional neural network. Don't worry about it. We are going to go over the details of it, but we are going to build this convolutional neural network which will identify which monkey among the 10 different monkeys to classify. All right. Now, here's the table of content. We will first download and extract the dataset. Then we will prepare the dataset and the configuration parameters for training. Then we'll show you how the data set is pre-processed, because some things need to be done to the data set so that it's ready for training. And then we will create a new convolutional neural network architecture in Pytorch, and then we will do model training and evaluation. And finally, we'll save and load the best model weights. And then finally, we'll do inference. Inference is nothing but predicting the response of the model on a new image, right? So whenever we do this prediction, whenever we use the model after training it, it is called inference. And finally, we'll go with the conclusion. Now we begin with showing you some of the dependencies, right? We'll have to import all these packages, Python packages, and these are very standard imports, but which are all available in Google Colab. Some of them may not be available in Colab. For example, torch info may not be available in Colab. And in that case, we simply uncomment this comment and then run this cell. You'll be able to install torch info in Colab. All right. So these are standard imports. We will not go over them because we have gone over them in previous notebooks. So let's go over this piece of code. The very first thing, as you have seen in other places also, we set the seed, right? We want to make sure that all the results that we are generating in our experiments are reproducible. If we do the experiment again, the same results are obtained, right? And that is done by setting the seed of the random number generator. And you can see that there are a few different random number generators that we need to set the seed for. This is the NumPy random number generator, the random number generator here, the torch. Inside torch, we have the CUDA random number generator, and so on and so forth. So we want to make sure that all of them are set to the same number, and they are set to one particular number. They didn't actually need to be set to the same number, but we just want to set one seed. Now, finally, after writing this function, we make sure that the seed is set to the number 42. You can use any number of your choice. If you know why we use the number 42, great points to you, extra points to you. Well, if you do not know why we set the number 42 as the seed, you should check up on your sci-fi reference. All right, this is a task for you. Next, we are going to download and extract this data set. As you can see that this is a data set of different kinds of monkeys. And here you have to uncomment this and run wget, right? Wget is the command line utility that allows you to download a file or a folder from a URL. So we are going to say, we are telling it to download this URL. This is the Dropbox folder in which we have kept the data. And then we are saying that, okay, name that file to 10_monkey_species.zip, okay? And in the next line, again, you have to uncomment this line if you do not have the data set ready with you. And this is going to unzip the data set for you, okay? This is going to unzip this file 10_monkey_species for you, okay? Next, we are going to set up the training configuration files, okay? When we train a model, there are a few different things that we need to be aware of. Now, the training set consists of many different images and the labels corresponding to those images. Okay. And when we train, we are going to create this class to configure our training. The very first thing you see here is the batch size. Okay. So when you are training on millions of images, right, you cannot load all those millions of images onto your GPU or your CPU because it's going to, you may not have all the memory needed. So you need to select a batch size. This is basically the mini batch size, a small collection of images that you will load in on your GPU and train the model at a time. And you basically select 32 at a time. In this case, the batch size is 32, and update the model weights. And then you keep doing this over the entire data set. Then you go over the data set again. Okay. So one epoch is when you have gone over the entire data set once. And remember that we are selecting 32 images at a time. And so if you your data set consists of 320 images, then you will have to go over all of those things 10 times, right? And once you go over 10 times, 32 at a time, you will complete one epoch, right? But even after completing going over the data set once, you're not done. You have to go over the same data set one more time. So it's an iterative process. You keep going over the entire data set multiple times because it gradually trains, it gradually improves, it gradually gets better and better. So we are here saying that we are going to use 50 epochs, which means that we are going to get, we are going to use the entire data set 50 times. We are going to go over those data sets. Then we have this parameter called learning rate, right? Learning rate basically controls how your model parameters are updated. Now, in a CNN training, what happens is in any neural network training, you have many parameters in a model, right? There could be millions of parameters, sometimes billions of parameters. And you can think of them as knob settings, right? When the knob is in the right position, the neural network is trained, you give an input image and it will give you the right answer. But in the beginning, the knob settings could be completely random, right? And our job in the training process is to find the right knob settings. And there are millions of knobs that we need to fix during this training process, right? So let's say when we pass a certain batch, right? When we pass one batch, the model needs to be updated based on how the model performs on this batch. We know the ground truth for this model, which means that we know which kind of monkey it is. And when once we see the response of this model, and we have passed 32 images, we may see that, okay, not all 32 images were correctly classified. And that error, right, that mistake the model made, it is sort of back propagated. So it is used to update the weights of the model, all right? Now, how fast the model weights are updated is controlled by this parameter called learning rate. Now, you may be saying that, why don't we do it as fast as possible, right? The problem is, you can think about the error surface as a bowl in a multidimensional space, right? Now, think of like a marble, right? Your error is going down in this bowl, right? If you go too fast, then this marble is going to overshoot the bottom and it is going to go away. It is going to diverge. So we don't want the marble to just run away. So we want it to be at the right speed, right? So we want it to be fast, but not so fast that it just escapes the bowl, right? So we want to get to the bottom of this error surface. Now it's a tricky one. Usually, 10 to the power minus 4 is a good setting. But if you see that your training error is not decreasing, it is just going haywire, you can decrease the learning rate, right? In this case, this learning rate works pretty good. Then we have other configurations for training. For example, log interval basically tells us how often should we log the response, right? Which means that we are noting down, we are putting all the information in a log file. How often do we need to do it? Here we are saying that every time, right? Every time you go through this data, log it. Test interval also says, it means the same thing, right? How often are you testing the performance of your model? And because we are training a very small model, we don't care. We are saying that test it every time, okay? And then we have the data root, which tells us where the data set is stored. Num workers is, we have set it to 5. It is the number of workers which are loading. This is part of the data loader. It tells you the number of workers which are involved in loading the data, the number of threads that are involved in loading the data. And the more number of threads you have, the better it is, because you're loading the data faster and you're also keeping the GPU busy, right? On the other hand, we also have to be careful. We cannot just put it to 100 or so, because then it will overwhelm your system. A number 5 is a very good choice. Next, we have the device. The device means, are you going to train the neural network on a CPU or a GPU? What kind of device it is, right? And here the device says CUDA. CUDA basically means that you are running this thing on a GPU, on an NVIDIA GPU, right? And that is why CUDA is basically the framework that they use. It is a collection of libraries that they use for their GPUs. The reason it's not called GPU here, because there could be different kinds of GPUs. There could be an NVIDIA GPU, you can have an AMD GPU, and so on and so forth. For NVIDIA GPUs, it is the device string is CUDA. Now, you can check whether you have a GPU or not by going to this connect, and then change runtime. And here you will see whether you have GPU or not. You can select GPU, CPU, etc. If you want to run this notebook on the GPU, you have to select a GPU, one of these GPUs. All right. All right. So that is the training configuration, right? And then we have this variable which creates an instance of the training configuration. The dataset configuration, we are taking it as the default one. And here, please note that the device, first it is going to check whether we have a CUDA device available, that is an NVIDIA GPU available. If it is not available, then let's use the CPU, all right? And here it's printing whether the device is available or not. And when I had run this previously, it said, okay, the device is available. All right, now let's load our custom dataset in Pytorch. So in the previous notebook, when we loaded the Fashion MNIST dataset, it was already available in the Pytorch Torch Vision library. And so this is different because this is generic. We just downloaded some data and we are going to use it in Pytorch. Now the monkey species dataset, right? I have downloaded it on my local machine. There's a CSV file called monkey underscore labels. And then we have a folder called training and a folder called validation. Okay. Now let's look at the CSV file, the text file first. It is actually, even though it is .txt, it is actually a CSV file, which is comma separated value file. You can see that the first row tells us what it is: label, Latin name, common name, training images, validation images. The label for the first monkey is N0, and we have these labels from N0 to N9. And we have the Latin names for the monkeys, and we also have the common names for the monkeys. And then we have how many images are there in the training set. It is kind of a balanced data set, pretty much the same number of images for all different classes, which is great. And we have validation images, again, about 26, 27 validation images. Now, training images are what we use for training, and validation images, these are a held out set. This is completely different set that we validate on, which means that we test the accuracy on the validation set and we use the training set for training. Now, you may be thinking, oh, why do we need to separate these things out? Because a neural network is so powerful that if you train on the training set and test on the training set, you will see zero errors. You can easily create a neural network because it's going to memorize all the answers in the training set. So to check whether it has learned versus memorized the answers, you have to have two different sets. You train on the training set, and validation set is independent of the training set. This is the part of the data set that the model has never seen, right? So we test on this unseen data, that is validation set. All right. Now let's look at some images, right? In the training set, we have another folder called training. I don't know why. This is just how the data set is arranged. And then we have these labels N0 to N9. These correspond to different monkeys. Inside N0, we have monkey 0. And you can see that this is whatever the name of the monkey is, I don't know. But the same monkey species you can see many images of it, right? And the same structure is repeated in the validation set. Inside the validation folder, there is another validation folder, which is just a little bit strange, but that's fine. And then we have in the test set, we have the same monkey, but not the same images. All right. So that's what the training set or the data set looks like. We have already gone over these things. Now, when we train, we have downloaded this onto this wherever this thing is located, this notebook is located. So we say that, okay, the training root path is 10 underscore monkeys and underscore species. And then there is training. As you can see, you remember that folder structure, there was training. And the same thing applies for the validation root. We have the top level directory and then validation. All right. So then we use pandas. As you know that when you want to work with CSV and other formats, reading text, pandas does a great job. So we are going to read the CSV using pandas, read CSV, and we are going to read this text file. And we know that it is a comma separated file. So we are saying that, okay, the separator is a comma. And then we have these columns, right? And then if you look at all the different, the data that is contained inside it, we are just listing out the data. And I have shown this data already to you in the text file. We're just reading it in a data frame. So this DF stands for data frame, right? We are reading it in a data frame so that now all the information is in this variable DF, okay? So now this is all straightforward. Next, we are going to calculate the mean. When we downloaded the dataset, this monkey dataset, the mean of all the images, right? This is the color mean, the RGB color mean, and the standard deviation is already calculated for us and given to us. And if you did not know what the mean and standard deviation of your dataset is, we have given, there is a utility function, we'll come to it in a little bit, that you can use, right? But in this case, we know what is the color mean and color standard deviation of the dataset. We also know the image size. If the image is not this size, we are going to resize the image to this size, all right? And you may be thinking that why is the image size 224 by 224? And this is for historical reasons. When AlexNet, one of the most popular, the most successful first model that won the ImageNet large-scale visual recognition challenge in 2012, when it was released, it used image size of 224 by 224, right? So that's the historical reason why we use image size 224 by 224 a lot. Okay, next we do some pre-processing, okay? So transforms.compose, the very first thing it is doing is it is changing the image size to 224 by 224 if it is already not that size. Anti-aliasing, it just makes, when you do the resizing, if you turn anti-aliasing equals true, you get a better image, right? It is computationally a little bit heavy, but you get a better image, okay? So next we convert all the images to tensor. Tensor is nothing but a multidimensional array, okay? So you can think about, an array of 3 by 3 by 4, it's a tensor, right? So 3 by 3 matrix, when it is 2D, then we call it a matrix. But if it is multidimensional, then we call it a tensor, all right? So next we are going to normalize the image. So all the images in our data set, they need to be normalized. And the normalization basically is we subtract out the mean from every pixel value, okay? And we divide it by the standard deviation for every pixel value, right? So here, as you can see that the mean has 3 colors, and the colors are basically from 0 to 1, right? In a standard image, you have colors from 0 to 255, but when we read these images, we divide it by 255. So the color range goes from 0 to 1. Now, for all the R channels in all the images, we are going to subtract the mean from the red. So this is the mean, right? For the red, green, and blue channels, we are going to subtract it. and we are going to divide the red channel by the standard deviation, this standard deviation, and the blue by this, and the green by this. All right. And why are we doing this? Well, this is a sort of normalization. When you subtract the mean, you're basically making the photo invariant to brightness changes. So some two pictures which are taken of the same scene, the brightness is different. If you do mean subtraction in that space, both the images become the same because the brightness is subtracted out. Standard deviation basically removes the contrast element. So if two images are taken of the same scene, they have different contrast. First subtract the mean and then divide by standard deviation. In that case, you will eliminate both the brightness changes as well as the contrast changes. So the images look much more uniform. Okay, that is why we do this normalization. All right, so next we are going to do some data augmentation. Now we have this data set, right, which contains about 100 and 10 different, about 1300 images, and in the training set. Now 1300 images, it's okay, but it's not great. So when we do not have enough data, or even when we have enough data, we want to create new variations of the data, right? So a machine learning model can consume a lot of data, right? These neural networks, they can consume a lot of data, and the more data you give, the more variations of the data you give, the better it is. So people came up with this idea of data augmentation. You come up with a data set, but then you augment it. You change the data set in ways that creates new kinds of data. For example, you can do a horizontal flip. Now a monkey and a horizontally flipped version of the monkey, both are monkeys, but to a machine learning model, these are two different pieces of data. Now you've simply doubled the data set size by using the monkey as well as its flipped version. Okay. Now you can also do something called random erasing, right? Random erasing was introduced in this paper where you basically, erase part of the data set. You have an image and you erase part of that image using random values. What happens with this is that this kind of augmentation is that the model that you train, it becomes robust to different kinds of occlusions, right? So if part of your image is not visible, it becomes robust to that. So it's not just learning, if you do this kind of augmentation, you can see that humans will have no difficulty in saying that this is a fox, right? In this example, where we have replaced this region by the mean value, we can still say that this is a fox. Here also we can pretty much say that it is a fox. So by changing random, obscuring random parts of the image, we are making the model more robust. So we are expanding the data set, we are giving it much more data, and we are making it more robust. Okay, so that's random erasing. This probability equals 0.4 means that 40% of the time we are going to randomly erase something in the data set, something in the image before sending it for training. Okay. And then we have affine transform. Okay, so you can geometrically modify an image, right? You can rotate the image and it is still going to be the image of a monkey, right? So here we are saying that, okay, you can rotate the image between 30 and 70 degrees. You can translate the image. Translate simply means that move the image in the X and Y axis. And we are saying that, okay, you can move in the X axis 10%, in the Y axis, you can move it 30%, right? And then you can scale the image. You can make the image bigger or smaller by half to 75%, right, of the original size. And you do this with probability 0.1, which means that 10% of the times you can apply a random affine transform. Affine transform is nothing but a collection of rotation, translation, scale, and another thing called shear. But here we are just doing rotation, translation, scale. Okay, so an affine transform is a combination of all of those things, and we are applying an affine transform to the image 10% of the time. Okay, and we are normalizing this image by the mean and the standard deviation, as I had mentioned before. So these are the different kinds of transforms we are going to apply to the image. Now we are ready to load our custom data set. So here we are going to use torchvision.datasets.image folder. This is the function that we are going to use to load all our data. Now it takes as input the root directory where the data is stored. Then it asks us whether we want to transform the data when we are loading it, whether we want to transform the images in certain ways. And yes, we have already defined our transforms. We want to, apply some affine transforms. We want to flip the data and so on and so forth, which we covered in just a few minutes back. Then it says whether you want to transform the target. Target is the label in our case. We don't want to transform the target. And then, those are the important things to keep in mind. So here you can see how we call it. We are loading the training data, train data. We are going to pass in the image folder, which in our case is train root. And then we are going to say that, okay, we want to transform our images as they are loaded, but we are not going to actually transform the labels. The labels are just fine. Similarly, we want to load our validation data. So validation data, val_data, and then we have the same syntax, all right? And then if we look at the classes, we look at the train data.classes, it is going to output these numbers, as we know that the labels are N0 to N9, all right? So, and then we can also look at the IDs. I mean, it's trivial. So you can do class to ID, and you can see that N0 maps to the number 0, N1 maps to the number 1, and so on and so forth. We can also check the length of the training data, and it can be done by simply checking the length of len of the training data, just as we do in Python. All right. So now I had mentioned that if you do not have the mean and standard deviation of your data set, then you can calculate the mean and standard deviation using this function. We already know the mean and standard deviation. It was provided to us when we downloaded the data, so we don't need to run this this function. But let's say you had a data, you had a data set and it's completely new. Nobody had used it before. You don't know the mean and standard deviation of the data. Then you can simply run this piece and you will get the mean and standard deviation. All right, so now we are ready to have our data loader. So we do train_loader. We use the DataLoader class to come up, and we pass it the training data. We say that shuffle the data. It's very useful. It's actually very important to shuffle the data because sometimes the data is arranged in a certain way, right? And if you don't randomly shuffle the data, you may end up in a situation where your data set has certain biases, right? For example, if your data has been acquired in a chronological way, so you will end up passing all the data on day one, let's say, to the algorithm while it's training in one set. We don't want that. We want the variety in the data to be passed. So when we pass in a single batch of image, that batch needs to have variety, and that is where we get good results, okay? So that is why we shuffle the data. We already know the batch size, we know the number of workers, and we just pass them along. The same thing we do with the validation loader as well. Next, we can do a sanity check whether everything has been loaded properly or not. So train loader, this is a data loader. It provides an iterable and we can iterate over it to get, and then we can get the next value so that we get one value out of it. And then this length, basically it is checking whether it has two values or not. Usually this is a good sanity check. You can simply do it. The length is 2 because we have the input data and the labels. Because of that, this thing evaluates to 2. Now we also want a class mapping. This class mapping between the classes, which is 0 through 9, and the kind of monkey it is, right? And this thing we have just created from the text file that came with the dataset, so that it's not interesting to know that it's class 9. We want to show Nilgiri Langur as the output, right? That is why we have this class mapping. All right. Then we have this visualization function where we visualize an image. We have the data loader. We say that, okay, these are the number of images. How many images do you want to display? And then we go and display those images. So this is standard Matplotlib way of displaying the images, right? If you go through the code, this is pretty easy to go through. All it's creating is a number of, it's creating a plot first, a 10 by 10 plot, and then it is creating, iterating over the data loader and getting the images and labels. And then we basically go over each image and then plot it, right? If you run this, you will see that all the data is loaded, and we are also putting in the the label, which is white-headed capuchin, and as well as the number, right, which number it is. So here we are basically displaying about 20 monkeys from the data set, right, just as a sanity check. Okay. All right, now we are ready to define our convolutional neural network, which will help us solve this problem. And as you can imagine, convolutional neural network consists of convolutional blocks, right? And let's go over the big architecture first so that you get a big picture. So this is the neural network architecture that we are going to implement. And you may be thinking that, how did you come up with that? And the thing is that you just come up with it, right? You have certain things you have to keep in mind. But other than that, it is a designer's choice what they choose. And there are some, some ideas people use on how to choose various blocks, etc. And these ideas have been developed over time. So we have selected some good ideas and put this together, but it's a designer's choice. There are many design choices that we have made here that a different designer would make a different design choice. But more or less for these simple problems, they will all produce reasonable results. Okay. So now let's first look at the input to this neural network. It is an RGB image. That is why we have 3 channels here. And the image is 224 by 224. And as we had seen before, if the image is not 224 by 224, we have to resize it to 224 by 224. All right. And then we have the output. The output of this is a vector of 10 numbers. And the elements of this vector, they add up to 1. Okay. Because these elements, they represent probabilities, class probabilities. So you could, for example, if you have trained this neural network properly, you could send an image of a monkey, a Nilgiri langur, which is class 9 on the input side, and the output you'll get is a vector of 10 numbers. And as we know that the last number represents the 10th class, so you will see some very small numbers in other classes. And this would be, the last one would be about, let's say 0.98, right? And this is the biggest in the group. And you will know that, okay, there's a 98% chance that this is a Nilgiri langur. And we will just assign it that class, right? So that is the output that you will get, class probabilities. And the class probabilities will be one vector from 0 to 9, okay? 10 dimensional vector where we have 0 through 9 classes. Okay, now you may be thinking that, okay, what is this thing? It is called a feature extractor. All these blocks here, they are under feature extractor, and these blocks are called a classifier. Now, in any machine learning task, we try to convert the input data, and the data could be in a variety of formats, right? It could be an image, it could be sound, it could be some kind of text. But if we are able to convert this input data into a long vector, and a vector is nothing but an array of numbers, if we are able to do that, then there are many machine learning solutions, right, which we can use to convert this vector into a class probability, right? So so here the vectorization of our input image is being done by this feature extractor, right? The job of the feature extractor portion is to extract interesting features from the image, which is useful for the task. For example, we want to classify a picture into one of these 10 monkeys. In that case, the feature extractor is going to extract interesting features from the input image, which will enable us to make this decision, right? The actual decision is made by the classifier, but the feature extractor will convert this image into a vector, and the size of the vector could be something like 512 dimensional vector. So what are these features? These features could be many different things. A color is a feature, an edge is a feature, a corner is a feature. So convolutional features, they extract, there are these filters that are applied to the image, and the response of these filters, right, they form the parts of the feature vector, okay? And then we have the classifier. So the image has been converted from 224 by 224 by 3 to a vector, right? Now we are going to use this vector and classify the image. All the information has been encoded into this vector, and now our goal is to classify it into one of these 10 monkeys, right? And that is the job of the classifier. Now you may be thinking that what do these linear layers, these parts of the classifier look like? Well, these linear layers, they are nothing but fully connected layers, as you had seen in the multi-layer perceptron notebook. So these are basically, in this case, for example, it has 256 inputs, and it's fully connected to the previous inputs, to the previous layers, right? So these are basically fully connected layers followed by a softmax layer, right? Softmax, as I had mentioned before, it converts these raw numbers into class probabilities. All right, and here at the last layer of this, we have a vector which is 3 by 3. We have a tensor which is 3 by 3, and then it has 512 channels, right? This flattened layer basically flattens it into a single vector of 512 times 9, whatever that number is. So that's what it looks like at this point. Now let's find out what do these convolutional layers, or the components of the convolutional layers, look like. So I'll go a little bit down in the notebook to show you here. So you can see here, this is the first convolutional layer. The input to this convolutional layer is our image 224 by 224 by 3, and the output is this one, right? Forget about the first the first element that corresponds to the number of images you have in the batch. So forget about this first dimension. The second dimension is basically the number of channels it has. So 32. There are 32 filters, convolutional filters, and the output size of this is 220 by 220. So we must, at every stage, if there is no padding, if we don't say that, okay, create the same sized image, because it's a convolutional operation, the size of the image would decrease. For example, here the size of the image decreased from 224 by 224 to 220. So you lost 2 pixels on both sides. So this must be a size 5 convolutional kernel, right? So we can see here when we are building it, a convolutional kernel with size 5, and the number of channels is 32. So this basically means, the first one basically means that we have these small 5 by 5 kernels. We have 32 of those, and we run the kernel on the entire image, and that creates one 220 by 220 image. Because the kernel size is 5, we lose the sides, right? The kernel needs to be on the image to do the convolutional operation. So we lose 2 pixels on this side and 2 pixels on that side, and 2 pixels on the top and bottom as well. So we end up with a 220 by 220 image. The number of channels, right? Each kernel, the number of channels is 32, because we have 32 different kernels, right, that are applied to it. So we end up with this shape, okay? The second thing inside that group, right, is a batch normalization layer. So we have the convolutional layer, which has many filters, right, 32 filters, and we have the kernel size, which defines what is the output size. Then we have the batch normalization layer, which stabilizes the training process. It has many different benefits, but the batch normalization process takes the output from a batch and then normalizes all the responses from 0 to 1 in that batch. Okay. And the benefits are, there are several benefits. We cover all of them in detail in our paid courses, but here it's difficult to explain because it's a short course. Now, after that, we have a nonlinearity called ReLU. So ReLU activation basically means that, okay, anything, any value. So we convolve this entire image with this convolutional kernels, and we may get values, all kinds of values, right? We may get some positive values, we may get some negative values. So what ReLU activation does, it leaves anything that is positive untouched, right? So if the value that we get is positive, leave it positive. If it is negative, it truncates it to 0, right? Now you may be thinking, why are we doing this kind of activation? The thing is that a neural network needs to have nonlinear activation, right? If you create a linear system where everything is a multiple of something else, in that case, the learning is not very effective, right? You can only learn so much, but it is the nonlinearity that modifies the data in such a way that you can learn better. You can learn many different representations. And again, unfortunately, I cannot go into the details why these nonlinearities are useful, but for now, because of the time is short in this course, but if you take our long format course, we explain all of these things in much more detail. But anyways, a convolutional block usually consists of a convolutional layer with many filters. Then we have the batch normalization layer. It has become pretty much standard these days. Then we have a nonlinear layer activation, which is ReLU is a very popular nonlinear activation layer. And so you can see that these three combined, they form one block. And then we repeat these blocks again and again, right? So we repeat another set of convolutional kernels, right? And after that, here we are doing pixel-wise processing, right? We are figuring out what are the features that we can extract on a pixel basis. After that, we want to do pooling of the features, right? So it's not just important that what's in a particular pixel, we also want to get the information from the neighboring pixel, and that operation is called pooling. You can do different kinds of pooling. You can take a piece of the image and you can do averaging of it, right? But most commonly, people do max operation. So it is a max pool. You take a 2x2 region of the image and you pick the max among them and you create the output. So this, if you go back to this image here, you can see that we have the convolutional block, which consists of a convolutional layer, a batch normalization layer, and a nonlinear activation. And then we have another one of those. And the number of filters in these blocks could be different. There could be different choices different designers make. And then finally, we have the max pooling layer, where the idea is to pool information from different pixels so that we are not just using information from one pixel at a time, right? So we are pooling information, and this is the max pooling layer. Now, this block is repeated multiple times in our implementation. You may be, wondering why did we use, two layers here and then one max pooling layer? Why did we make these exact choices? And the answer is that, it's a designer's choice. There is no good way to know which one is the best, right? We could have used 5 convolutional layers here instead of 4, in which case the learning capacity of the model would be more, but it may have other downsides. Similarly, so all these choices are made by the designers, and that is why it is complicated, right? How do you choose these things? Turns out that usually in real world applications, you don't have to make these choices. You usually take an architecture which has been tried and tested by many people. It has been designed by people at, let's say, Facebook and Google and others, and they have tried many different options and come up with the best thing that works for the largest number of people. And we can just pick that model architecture and then fine tune it. Okay. But in this notebook, we just wanted to show you how it is built. And that is why we are going into the details of these options. All right. So basically, when we have these banks of convolutional layers, these form feature extractors, right? We are able to extract the important things in the image which help in the classification task, right? So that is the reason for this block. And then finally, we have this adaptive average pooling in the end. It is also a pooling layer. But the reason to add this is if you want to have a fixed output, then you use this you use this pooling layer, and we'll come to that in just a bit. Now let's look at how to build this neural network in Pytorch. So we start with this sequential a class which allows you to create one layer at a time. Okay, so inside this, the first layer is a convolutional layer, as we had seen before. The input channels is 3 because we are using a 3 channel image. The output channels is 32, and this is fixed by the designer. We could have chosen 64, we could have chosen 16, or any number we wanted, but 32 is a reasonable number. And then we choose the kernel size. So each of this convolutional kernel would have a size 5. So this is a 5 by 5 convolutional kernel, and we have to estimate all the parameters inside this convolutional kernel. And this convolutional kernel basically slides over the image to produce an output. And because it's a 5 by 5 image, you can imagine that to fit it inside the image, right? When you have a larger image and you have this kernel that needs to fit inside it, you will lose 2 pixels on the side for every output, right? So the output of this is 220 by 220, okay? Then we do a batch normalization. We have to specify what is the size of the batch. And here it is 32 because this thing is 32. And then we have finally a ReLU activation, which is a nonlinear activation. And these blocks are going to be repeated again and again. You can see that we again created this block. And then finally, we say that we want to have a max pooling layer. Max pooling also, you need to specify the kernel size. The kernel size in this case is 2 by 2, which means that the size of the image is going to be approximately half, because we are going to take all the values in a 2 by 2 neighborhood and convert that to a single value. So the size of the image would be approximately half of the original size as the output. So we have these two corresponding to here. So we are at this point right now. Okay. Then there are other ways of creating these layers as well. One of them is lazy 2D. The reason we are using lazy 2D, we could actually continue doing this, but lazy con 2D, it allows us to not worry about what is the size at the end of the previous one, right? So here the size of this is 109 times 109, and then there are 32 channels. These con2 we are going to build using lazy con2 because we don't know. I mean, we know because we have done the calculation, but let's say I'm lazy. I don't want to calculate what is the size of this. Then I can simply use lazy con2. As you can see here, it says, don't worry about the input channels, right? In this case, we needed the input channels, right? Initially, the input channel was 3, and this produced an image which had 32 channels. Then we specified using this one that, okay, we want input channels 32. Now I get lazy, and I say that, oh, I don't want to figure out what was the input channel in the previous one. I'm just going to specify the output channel, and Pytorch will figure it out itself. So that's lazy conv d, and we also need to specify the kernel size. And the same thing goes again, right? So we have the batch normalization layer. and so on and so forth. Here again, we don't want to specify the input channels because we are lazy, and we create this another layer. The layers that are created using batch norm 2D, conf 2D and lazy conf 2D, they are exactly the same. It is just that in this case you have to specify the input channel. In this case, you don't even have to specify the input channel. It figures it out by itself. So and then we have again the max pool layer, and we are at this stage right now. Okay. There is a third way. There is a third way to do this, and we are just showing it using different methods available in Pytorch, so that when you see these options, some people like to code in certain ways. You will see some people using this kind because it's very clear what's going on, but some people would simply use conf 2D norm activation. This basically means that it is these three lines have been combined into one, right? Here you have to specify the input channels, the output channels, and the kernel size, and it is going to do exactly this one line of code is exactly the same as these three lines of code. All right, so you can do that, and then we have the second convolutional layer, and then we have a max pool layer, and finally we have the third one, right? And we have a max pool layer. So going back to this, we just did the third convolutional block, and then we did the fourth convolutional block. And after that, we did the adaptive pooling. Again, adaptive pooling is used when the output height and width is something that you want a specific size, and you don't want to worry about the input. That's when you use adaptive pooling. So here you can see it says adaptive average pool 2D, and it just specifies the output channels. It doesn't specify the input channels. The code inside Pytorch automatically figures it out what should be the structure, so that the output is 3 by 3, right? The height and width of the image after this is going to be 3 by 3. Okay. And finally, we flatten the layer. Like as I had mentioned before, this layer is going to be flattened, which means that whatever vector comes out here, the output is 3 by 3. Size of the channels is 512, and it will be flattened out into something which is 512 times 9. Okay. And finally, we have these linear layers. Okay. So that is our neural network, and then we'll attach the softmax function to it. But there are two linear layers, as we can see here. This we have flattened it, then we have linear, and then we will in the end we will add softmax also. Okay, but softmax is not part of the neural network because that's it is just for displaying the output. Okay. So now we have created this model, right? And we also define a forward pass. Forward pass means that you have an image and you pass it through the neural network and get an output at the end of the neural network. That is called a forward pass of the neural network. Okay. Now the backward pass, why would you do a backward pass? Well, the backward pass is used during training when you want to update all these weights of these models. The convolutional kernels that you used, the values inside those kernels, they need to be exactly right. They need to be good so that you get a good output. And based on the errors that we see in the output, when we do a backward pass, which is basically an algorithm called backpropagation, when we do a backward pass through this network, we are able to update all the weights of these convolutional layers and these linear layers, and that is how you basically get the output, right? You get the weights to update, and the output gets better and better over time, right? That is what backward pass looks like, and the forward pass is simply running this image through the neural network and getting an output here. Okay, so here we have the forward pass, which basically says self.model x. Basically the model is run in this way. All right. Now, to train the model, we need one more thing. We have the data, we have the model architecture, and then we need to define an optimizer. You may be thinking, what is an optimizer? Well, an optimizer is something that allows you to update the weights of the model, right? So as I mentioned, that all these filters that we are using, they have certain parameters, and they need to be updated. And the way to do that is, how do we know how to update the weights, right? I mentioned that we need to use an algorithm called backpropagation, which is fine, but there are other things that we need to consider also while updating these weights. How fast does the model get updated? Is there a clever way we can update the model so that it minimize the error in a faster way, right? So all those things uh, are implemented in an optimizer, right? And one of the very common optimizers, it is called ADAM, right? It is adaptive moment-based optimizer, which you don't need to know the details yet. We cover these things in our paid courses, but for this short course, it's impossible to cover everything. So keep in mind that this basically helps you update the weights of the model. It is essential for training the model. So for training a model, we need three things. One is the data, right? We need to load all the data, which we did. We need to define the model architecture. And finally, we need to define an optimizer, which will help us, okay? So this optimizer, it takes in all the model parameters, and it also takes in the learning rate, right? How fast the model should learn. And as I had explained before, if it learns too fast, it may actually miss the minimum of the error surface, and we don't want that. But at the same time, it should be fast enough. So we have to select it properly. And the model parameters, these are, we have already defined what are the model parameters. So next we need to define a device, as we had already looked at the code, we are going to select CUDA if CUDA is available. This is nothing but NVIDIA GPU. And if CUDA is not available, then we go with the CPU, all right? And if you have other kinds of, you can use a TPU, and which is a tensor processing unit in Colab provided by Google. You can change this to use TPU as well. The logging will be done in this directory. Usually you pick a name of the log file name should be such that it represents the experiment that you're doing. Then you have, you have a summary writer, which basically looks at this log file and extracts the summary of what was done, okay? Okay, so now we are ready to pass a dummy input. So our dummy input is this tuple, which is 3 for 3 channels. And this 224 by 224 is the size of the image. And we are going to run it, right? So we are going to do model summary. So we are going to find the summary. We are going to use this model. We'll give the dummy input, and then the row settings are variable names, and the device is CPU. We are going to run it on the CPU. And out comes this text that we went over. It gives you a summary of the model, right? So it gives you the summary of the model that we have. And this is a very good way of knowing what is the model. This also verifies us, okay, the model that we created, is it according to our specification, right? So here you can see, all these various layers that we went over. And as I had mentioned before, right, const to the norm activation, it is nothing but a combination of these 3 layers, right? And yeah, so that's about it. It also gives you the total number of parameters. We have 3.35 million parameters in this model, and all of them are trainable parameters. There are architectures where not all parameters are trainable or don't need to be trained. That's pretty much what you want to know in this section. All right, so until now we have loaded our data, we have checked the data, we created a new neural network architecture, We checked whatever we have created is proper using the summary command. And now we are ready to train our neural network. Okay. So here's the training code. Uh, the very first thing we need to do is set the model in training mode. Now, there are two modes of this model. One is training mode and the other is inference mode. During inference, we don't need to calculate a lot of things that we need to do during training. And that is why we need to explicitly set the model in the specific mode. So we said that, okay, the model is in training mode now. And then we send this model to the device. The device is the CPU or the GPU on which you're going to train the model, okay? Running loss. Loss basically means, it's a function of the mistakes you're making. If the loss is high, you're making a lot of mistakes. Your model is making a lot of mistakes. And if the loss is low, that's a good thing. Okay, we want the training loss to be less. Then we are setting these variables, correct predictions to 0, total training samples to 0, and then we are going to loop over all the data that we are getting from the data loader. Now, this is basically setting up the progress bar, and then we are getting a set of images and a set of labels from the training data. Now, these images and labels, the number of images and labels will depend on how many images are there in the batch. In our specific case, the batch we have selected is about 32 images, not about 32, exactly 32 images. And so we will get 32 images and 32 labels. These images we are going to send to the device, and the labels also we are going to send to the device. Now you can imagine, if we do not have this mechanism of learning in small batches, we could be sending millions of images and the GPU would not be able to load all the data in memory. And that is why we need small batches. But there are other technical reasons also for using small batches. It is actually good. Even if you had the option of loading very large batches, you should not do it. Mini batches help in training, which I cannot go into the details in this video, but it is a good idea to have small mini batches, right? Something like 32 or 64. Next, we need to set the optimizer. All the gradients need to be zeroed out. So when the optimizer runs, it calculates the gradient, and these gradients are important for this algorithm that I told you called backpropagation. And in Pytorch, by default, these gradients, they don't get reset after every iteration, right? So we want to make sure that it is set to 0. This is a very important step. If you forget this, you'll get very bizarre results. So, okay, we set the gradients to 0. We now have the output. The model is, when we do this, this basically means that we are doing a forward pass on the model. We are sending all the images to the model and doing a forward pass, and we get the outputs, right? Based on this output and the label, right? So we also know what is the ground truth, what should be the output, because the labels tell us what should be the output. And we have this output that the model has generated. They are not going to match. They are not going to be exactly the right ones. The model is going to make a lot of mistakes in the beginning, especially if we initialized it with random numbers. The model will make a lot of mistakes, okay? Now you take the difference, or you take the cross entropy loss of these two things, which is basically, imagine a function of the mistake it is making, right? You could, so this cross entropy loss, I'm not going to go into the detail of it, but what it will do is, when the label and the outputs, they are exactly the same, then the loss would be 0, right? Otherwise, you'll have a larger loss. But it also kind of saturates, right? Let's say it's making a very big loss. It doesn't mean that it's going to infinite. So it is going to saturate to a particular value, okay? So now we have calculated the loss, and you can think about the loss as some function of the error, the mistake it is making, okay? With the loss, we do a backward propagation. As I said, that the model now needs to be informed that, okay, change your parameters because you're making a lot of mistakes. So And these are the mistakes you have made. You have made a big mistake now, and go and update your parameters so that the next time the mistakes are small, right? And it is done in a very principled way, right? Not just, okay, one way to do it would be, okay, randomly change the weights now and see if the loss went down, right? And if the loss goes down, then you keep the parameters and then randomly shuffle it again, randomly change them. And if the loss goes down again, then keep it. If the loss goes up, then discard it and keep the original parameters. You could do that, but that's very, very expensive to do. You will wait for eternity for that to work. A mathematically principled way of doing it is called backpropagation, and this algorithm, it knows how to calculate the right, how to move in the right direction so that your loss is lower, right? So you basically do a backward pass, and then the optimizer is called to take a step, right? So the optimizer decides, the loss is decided by this, the difference between what we expect and what the model is outputting. And then we do this backward pass, but the optimizer decides how big of a step needs to be taken that we have already set, right? And there are, over time, initially it could take big steps, and then finally it can be set up so that initially it takes big steps, but gradually it takes smaller and smaller steps as it gets closer and closer to the real answer, right? So all those things are controlled by the optimizer, but here we are just telling the optimizer to take one step, right? And based on the settings of the optimizer, it will take the step. It could take a large step, it could take a small step based on the settings of the optimizer. Then we add up all the loss. We take the loss and add them up all, and then we do a prediction. So the output that we have got, right? We can take the output, as we know that the output determines. It's basically telling you, it's a 10-dimensional vector which tells you what is the probability of each kind of monkey, right? So we are doing a max on that to get the predicted value, right? Whichever is the maximum, we are saying that, okay, that is the monkey, right? That is the monkey category. And then we do some house cleaning, and we find the number of correct predictions, right? So you keep running this in a loop, and you keep seeing how many correct predictions it is making. And based on the number of correct predictions, we also can calculate the training accuracy. So training accuracy should actually go to very small number, right? You can make it go to almost zero. Now let's look at we'll go over the validation code also, but let's look at what happens during a training run, right? So when you run that, you will see that the training is progressing, and we had put in the progress bar, because of which you can see this progress bar. And here you can see that during training, the training loss is this much, right? This number you cannot make. It could be pretty much anything, right? You cannot say that, oh, it's the training loss is going to be between some bounds. So don't worry about this number. The only thing you have to look at it is that this number should be progressively going down over time. The training accuracy is 32%, right? Or nearly 33%. In the next run, right, when it takes the new batch, before it takes the new batch, it updates the weights, right? The filter values, it updates. And you can see that the training loss is progressively coming down, right? And the accuracy is increasing, right? So these are kind of correlated. You can see that the training loss is gradually coming down. Over time, the training loss keeps coming down and the accuracy keeps going up, right? And let's keep looking at it, okay? The training error, the accuracy is 94%, 95% here. It goes to, about 95%. The biggest number we get is 95%. So if you look at the training loss, right? The training loss, this blue curve shows the training loss, and it is going down. And at the same time, the accuracy is going up, right? This is expected. Let's look at what's happening to the validation loss. Now, the training error is going to be very good because it doesn't depend on you're showing you're showing the model the all the data, and it's training on the data, and that is why the training loss, it's going to get very, very good at recognizing, because it's being trained on that data. So the real accuracy though is measured on the validation set, because that is the part of the data that the model has not seen. All right, so let's look at the validation code. Okay, we went over the training code. All right, so now the validation code is very similar. It will look very similar to the training code, but during validation, when we are trying to find the accuracy of the model on the validation set, we don't need to do back propagation, because we are not checking, we are not using the validation set to improve the model. We are only checking whether the model is performing correctly. Okay, so the very first thing we need to do is we need to set the model in evaluation mode, which means that there are two modes that exist. One is the training mode, the other is the evaluation mode. Okay, so during evaluation mode, a lot of gradient calculation, etc., which help improve the model, that's not run, because we don't want this validation set to make the model better, right? This is a held out set. We just want to test the accuracy. Now the model is set to sent to the device, and then we iterate over the validation set, and we make sure that no gradients are calculated, and then we get the outputs, and we basically report the validation accuracy, just like we did for the training accuracy, right? So this is straightforward. Training and validation, these two things look very similar, except in training we calculate the loss and back propagate to improve the model. During validation, while measuring the validation error, we don't do any of that. All right. Okay, so now we have this main function. Those functions I've already explained. We have the training loss and validation loss, training accuracies, validation accuracy, and then we go over the data, right? We, as you can remember, epoch is the number of times the entire data set is consumed, right? So if you say that the number of epochs is 50, it means that your training program went over the entire data set 50 times, all right? So we say that, okay, for epoch and range, we want to go over the data set that many times. We calculate the training loss, we calculate the validation loss, and remember the train function goes over this entire thing, right? And then we find the training losses, we have the training accuracy, we calculate the validation losses, etc. And then we use this logging mechanism. We use the writer to basically log all the information. And if validation accuracy is better than the best validation accuracy, we are basically storing what is the best validation accuracy till that point. And we are also storing that weight, because these over time the accuracy is going to improve, but because we are using mini batches, we are not using the entire data set, we are using a small data set, it is possible that the accuracy fluctuates a little bit, as we can see in this graph. Let's see. Okay, in this graph you can see that over time it is decreasing, right? But at any point it is possible that you may not get to the weight updates can actually make the model a little bit worse, right? But over time, generally speaking, it is going to get better and better, but you need to keep track of what was the best model you had. And that is what this piece of code was doing. Okay. So we are coming to an end, right? So once we have described this, we basically calculate, we call the main function, we get all the losses and accuracies, which we need to plot these graphs. And I'm not going to go over the plotting function. It is pretty straightforward, and you get these graphs, right? And as I had said, that you should basically save the best model, and then you can do the evaluation of the best model. Now, model.eval would just give you the structure of the entire model. It will give you what were the different parameters, etc., inside the model, and so on. Now, if you want to do prediction on this model, right, it is going to look very similar to what the code that we wrote for the validation set, right? So if you want to do a prediction on this model, you have to set it in evaluation mode. You have to then move it to the device, and then this validation loader, we are going to get all the images from the validation loader and basically output the result, right? Nothing fancy here. Before we visualize our results, we need to write a small function to visualize the results. Here, this visualize underscore predictions does the job for us. We first set up a figure, and then we basically select a random number from a random image from the set. And when we select that image, we also want to make sure that the image is in the right format. So in Pytorch, the format is the channel comes first and then the height and the width. But for us to display the image, we want the image to be in the height, width, channel format. And this transpose function accomplishes that. So we have an image which is right for displaying in matplotlib. We get the label, we get the prediction index, which is what class was predicted. We get the probability of that class, and then we do a denormalization of the image. Now keep in mind that when we loaded the data, we also transformed the data so that we had removed the mean from the image. We divided it by the standard deviation. So we need to do that denormalization, which we do here. So you can see the mean, we got the mean, all the mean, we got the standard deviation, and we are creating a long list of standard deviation from it, and then we basically multiply the standard deviation and add the mean back in, because initially we had subtracted the mean and divided by the standard deviation. We are reversing the process, and once we do that, we also want to make sure that the image results don't go beyond 1. This should result in an image which is between 0 and 1, and because of numerical errors here and there, sometimes it goes above 1 or below 0, and we want to avoid that. So the clipping does that for us. All right, so now we are ready. We got our image, we denormalized it, and we are just going to display it, right? And when we do that for this, we find the predictions, and then we visualize the results. This is what the result looks like, right? This is amazing, right? The ground truth is bald Wakari, whatever that is. And the prediction is also that, right? So we got the right prediction, and the probability is set to 1. Here the prediction is, we still got the right answer, but the probability is a little lower. We got the right answer here, got the right answer again, and the probability, depending on the confidence, the probability could be in the 80s, sometimes even in the 70s. As long as it is the dominant one, we can say that we are going to select it. Okay. Sometimes when we have a small number of classes, we also want to summarize the results in terms of a confusion matrix. A confusion matrix looks something like this. So you can see that these are the targets, and here we have the predictions, right? So target means that, okay, for class 0, when the prediction is 0, 22 times that happened, right? So we want the confusion matrix to have all high numbers here, which means that these correspond to, the diagonal corresponds to the right result, right? Now let's look at off diagonal elements. Here it says that, okay, when the target was actually 0, one of the times it was predicted to be monkey of category 2, right? So the monkey of category 0 was categorized as monkey of category 2 one number of times, right? So if the number was very high, right, then it would suggest that the two monkeys look very similar. Now let's see here, this number is very high, right? So when the target is 5 and this thing is 9, the predicted value is 9. A lot of times, like thrice, it happened. It means that it is possible that the monkeys in category 5 and monkeys in category 9, they kind of look similar, right? So, that confusion matrix tells us something about how close different monkeys look to one another. Ideally, we want the confusion matrix to be a diagonal matrix with all other off-diagonal elements set to 0. Okay. So that pretty much brings us to the end of this video. I hope that you learned how to load your custom data in Pytorch. Then we learned how to develop a convolutional neural network architecture. We learned a few concepts, what constitutes the architecture of a convolutional neural network. Then we learned how to train the neural network. We learned how to evaluate the neural network. And finally, we learned about concepts like confusion matrix. So that brings us to the end of this video. I hope you liked it, and we are going to have even more exciting practical work in the next few notebooks. Now keep in mind that this particular technique that we showed you, you're almost never going to build a neural network from scratch in the real world. This was just an exercise so that you can understand how it is built, what goes inside the neural network. But in most cases, you are actually going to fine-tune a neural network that has been designed by somebody else so that you come up with a good solution very fast. So we will learn those in the next few notebooks. All right, thanks.